right, welcome to another podcast. In this episode, we're going to be taking a look at a very important result related to Wronskians called Abel's theorem. Now, Abel is a Swedish mathematician that was very famous for his work in many areas, but this is one of his more important results. It basically relates the Wronskian of a differential equation, the Wronskian of the solutions y1 and y2, to being one of two possible values. Either there's a specific value of x which makes the Wronskian 0, in which case all values of x make the Wronskian 0, or the Wronskian is never 0 regardless of the value of x. So how can this be used to our advantage? Well, first off, this one would say that y1 and y2, so this condition would say that y1 and y2 are linearly independent. We saw this on the previous video with the equations e to the r1t and e to the r2t for distinct roots. We saw that the Wronskian was not equal to 0, and in fact, it was not equal to 0. The Wronskian of these two things was not equal to 0 for all t. It didn't matter what value of t I plugged into it. I was never going to get the Wronskian to be 0. So that is case 2. Case 2 says that if there's not a single point, if there's not a point that you can find that would make it 0, then it's not going to be 0 at any point. You don't have to keep looking. If there's one single point where it's non-zero, then it is non-zero everywhere. Conversely, number 1 says that if the Wronskian of y1 and y2 is equal to 0, then the Wronskian of y1 of x, y2 of x, remember y1 and y2 are functions of x in this regard, this implies that they're equal to 0 for every x. All that means is if you find one x for which it's 0, then every x you plug in, it'll be 0. And so that's a very nice sort of either or, and what I actually want to do with this particular problem is I actually want to do a proof of this result. Now, it's not very often that I prove things, but this is an important enough result, and we're going to use this result in several different ways, but it's an important enough result that I think it bears a little bit of our time in trying to prove it, to understand the proof. Okay? So let's think it through. They are both solutions, y1 and y2 are both solutions to this differential equation. And what that means is that y1 and y2 solve the ODE, which means when I plug them in to the ODE, they both give the same answer. So all I'm doing is I'm taking and replacing y in the differential equation with y1 and y2, and I know because they're solutions, they have to make the equation equal to 0. I've got no choice here. So I want to do a little bit of algebraic manipulation here. I want to take and multiply the first equation by minus y2, and I'm going to add it to taking the second equation and multiplying it by y1. Now, you've seen similar things to this done before when you're solving systems of linear equations. And what is the result? Well, if I take and multiply these, notice that's going to get rid of the q term. So that's the whole point here, is I'm eliminating q. So that's the reason for doing this. So we're eliminating q, and the result is looking at something like y1, y2 double prime minus y1 double prime y2. That's what we get from this first piece, adding it together. And then the second piece, if we add it together, is we get the function p. Now the function p here is a function of x. So I'm assuming that P and Q, because this works even if they're not constants, I'm assuming here that both P and Q are functions of x. We'll look at equations like this a little bit later, about 2 weeks from now. Up till now, we've been considering only P and Q as being constants, but it turns out for this theorem that I can let P and Q be functions of x. And so if we do that, then what we wind up with here is y1, y2 prime minus y1 prime, y2 equals 0. And what I want you to realize here is what we're staring at is the Wronskian. This thing right here is the Wronskian of y1 and y2. And if I take its derivative, then it ends up being this. So this is something that you need to verify. But if I take the derivative of that term, so if I take the derivative of y1, y2 prime minus y1 prime, y2, so if I take this derivative, I've got to do two sets of product rule, but I'm going to get things to cancel. So this is y1 prime, y2 prime plus y1, y2 double prime minus y1 double prime, y2 minus y1 prime, y2 prime. And you see that when you take the derivative here, you get the single derivatives to cancel, which leaves this, which showed up right here. And so the point is, this leads to a differential equation where I have w prime plus p of x w equals 0, where I'm replacing these terms with the Wronskian instead. And so this is a differential equation which we should all know how to solve in here at this point. It's this differential equation, which has an exponential solution. So the solution to this equation is of the form a times e to the negative integral of p of x dx. And so I ask you, where have you seen this before? And your answer should be, this looks awfully familiar to something we would have called the integrating factor back at the beginning of the course. And in fact, it's intimately related to that. Remember, that's the way we solved those first order linear differential equations. And this is really related to that. But the more important thing is I can use this to prove the theorem. The reason I can use this to prove the theorem is, when is this going to be equal to 0? So if you look at this formula, this is a formula for the Wronskian, by the way, so don't forget this formula. If you look at that formula, there's two possibilities. Either a is equal to 0, in which case w is equal to 0, or a is not equal to 0, in which case w is not equal to 0, regardless of what x is. And that's what the theorem says. The theorem says that if w is equal to 0, it's equal to 0 for every value of x, and the only way that can happen is if that constant a happens to be 0. And the other possibility is, if that a is not 0, then it doesn't matter what this value of x is in the problem. The result is going to be that the Wronskian is not going to be 0 because it's based off an exponential. And so this is a very important result. What you need to remember is, if you evaluate the Wronskian at a single point, you can determine everything you need to know. Because if that single point turns out to be non-zero, then you know everywhere it's non-zero. If that single point turns out to be 0, then you know everywhere it's 0. So this is an incredibly useful tool that allows us to simplify some of our calculations involving the Wronskian. All right, thank you for watching.